Okay, our first lesson. All right, so you're going to start by using your protractor. You should have had one on your desk. If you did not, raise your hand and I'll give you one. Anybody not have a protractor? Okay. We're going to draw point B to the right of point A. So somewhere over here, you're going to put a point B. To the right of point A. Yep. And then we're going to define point. So, what do you guys think is a point? Yep. Like a dot. Okay. Good. A specific location. Anybody else? How many dimensions does a point have, do you think? Like 2-dimensional, 3-dimensional, 1-dimensional? What do you think it has? So you think it has length and width? Okay. If I draw a dot on my piece of paper, could I measure the length and the width? Yes. So here's where this might be a little different than what you learned before. A point, by actual definition, is an exact location in space, and it has no dimensions. There is no length or width. It cannot be measured. So we represent a point using a dot, which is 2-dimensional, but it is really just a representation of this concept in geometry of an exact specific location in space. So if you're having trouble sort of realizing what that means, I'd like to draw your attention back here to the backboard. There's this orange piece of paper here on a blue background. At the corner, is there any space between where the orange ends and the blue starts? Any space in it? No, that's a point. The exact location in space where it switches from orange to blue. There's no dimension there. It just is a place. It's a location in space, okay? Okay, now use your straight edge and draw a line through points A and B. And we're going to define line. So how would you define line? Yeah. Okay, infinite points. Good. 1 dimension, meaning length. It's in a plane. Okay, good. What else is a really important property of a line? It needs to be straight. Yes. Good. So a line is a straight, infinite collection of points. So how many dimensions does that have? Just length. Yep, 1-dimensional. So we represent it by drawing this line on our paper with an arrow on each side. But again, it's just a representation. Obviously, we can't draw a line that goes on forever, never, never, never. But conceptually, lines do go on forever, never, never, never. Okay? When we draw this line, could we actually measure how wide that is? Sure. But again, that's just a representation. An actual concept of a line has no width, just length. It's a collection of points. So if you think again about that orange paper there, it would be like the edge of the paper that goes along the blue. Okay, notation in geometry is really important. So you have to kind of learn what all the different symbols mean, kind of learn the language. So a notation for a line, this would be called line AB. And we use this symbol over it with a bar with 2 arrows, one on each side. You've probably seen this before. But in this class, we get really specific about different notation for different things. Okay, so a line has the two arrows, representing the fact that it goes on forever in both directions. We could also call this line BA, because a line has, how many points are on a line? Infinite, right? We've named 2 of them on this particular line, but there are infinite. So when we name a line, we only need 2. Never use 3, 4. It doesn't matter how many they name on the specific line you're looking at. Just pick 2, any 2 in any order. Okay? All right, now if we draw another point on this line to the right of B, and we'll call it C. Well, now this opens up more ways to name this line. If I could pick any 2 points in any order, how else could I name this line? Jack? CA or AC. Never 3, only 2. But which one could we, there's another way we could name this, yep. Good, BC or CB. Now, if I put another point on this line, now I'm going to open up a whole new, possible ways of naming the line. There are going to be a lot of them. Okay. There is one other way they sometimes name a line, and that's using a script letter kind of off the line somewhere. Notice these letters are naming actual points on the line. Sometimes they'll put like a script letter kind of off the line somewhere, and then that could be called line M. It could be line P, line Q, line R, line T, whatever. It's just a script M. Yeah. It's okay. It's okay. Do a regular M with a little on the end. I know, but it looks a lot like a regular M. Okay. This next word is collinear. I didn't leave you enough space for this, so don't write too big. Okay. Collinear. What does CO usually mean? Yep. Like together, right? Co is like together. Sometimes 2, sometimes more together. So collinear means objects that can be contained by the same line. So things that are together on the same line. So in other words, in our diagram, an example would be points A, B, and C are collinear. Okay, now we're going to use your straight edge again and draw another line that goes through the first line at point B. So it's going to go through point B. You're going to put a D up here and an E down there. So these 2 lines intersect. How would you define intersect? Robbie? Yeah, so 2 lines meet, they come together. Where do you hear the word intersection out in the real world? Melanie? Yeah, 2 roads, like a 4-way stop, or a stoplight is usually at an intersection. right? Where the two roads come together, right? So by definition, though, in geometry, specifically, it doesn't have to be just two lines. Don't worry about it. It happens all the time. Don't worry about it. Thank you. No, it's not your fault. It's all good. It's fine. I think it was already broken. Yeah. Okay. By definition in geometry, the intersection is where all the points that two things have in common, or three things, or four things, doesn't matter. But so all the points in common. So often we think of two lines that intersect, but it can be like a circle and a line. What's the intersection of a circle and a line in this diagram? Ewan? Okay, and what would they be at a point here and a point here, right? So the intersection, if they said name the intersection of this circle and this line, you would name 2 points. The intersection of, let's say, this segment and this segment, if I drew them actually on top of each other, which I wanted to show a little difference there, but if they were right on top of each other, what would the intersection be? All the points they have in common would be from where to where? From C to B, right? So that entire overlap, this entire section, would be the intersection. Okay, so in geometry it's a little different than just on the roads out there, right? Okay, so there's a postulate that says if two lines intersect, then their yep, we're going to define that in a second. If two lines intersect, then their intersection is a point. So if two lines intersect, then their intersection is a point. So that word if kind of infers that two lines don't have to intersect. Can you think of an example of two lines that do not intersect? Colin? Okay. Parallel lines, right. Two lines that go on forever, right next to each other, same distance apart all the time, never intersect. Parallel lines. There's actually another type of lines that don't intersect. The definition of a postulate is a fact that we accept as true without proof, without a formal proof. Okay, you guys all have heard about in geometry we write proofs, right? And we haven't learned those yet, but there are going to be a lot of things that we can write step by step and show exactly why this is true. And then there are things that we just accept as true without a proof. And that's what a postulate is. So two lines intersect, their intersection is a point. We're just going to accept that. Okay, in the diagram that you drew, this is all in 2 dimensions. We've talked about dimensions a little bit, right? It's got length, it's got width, it has no depth. If we were to add a 3rd dimension, we would be extending outside of this plane, right? So this is all in one plane. To define plane, we're going to call it an endless flat surface. It goes on forever in all directions. How many dimensions does that have? Well, directions infinite. Dimensions only 2. Has length and width, still no depth. In order to get depth, you're going to extend beyond one plane. Okay? An example in real life of a plane I always use the same example because it's about the only time I've heard people talk about it. Well, architects and stuff sometimes talk about planes, but most commonly in football. If you ever watch a football game, you might hear the announcer say, oh, you know, they're checking if the ball crossed the plane. Because in football, if there's the goal line and there's this imaginary plane that kind of comes up from that goal line, extends forever, and if there's a pile of football players and one guy has the ball and he jumps on top of that pile, what they need to do is kind of look from the side and see, did that ball actually cross that imaginary, you know, plane that extends up from the goal line? If it did, it's a touchdown. If it didn't, it's not. Okay, if two planes intersect, so imagine this front wall is part of a plane, right? It extends forever in all directions, but we see just part of it. And then there's another wall that's another plane, and they come together in the corner there. So if you can imagine these things going on forever and coming together, what would their intersection be? Okay, so good answer. A vertex is going to refer to just one point, so like two rays that come together at a vertex. And that still would just be a point, though. So let's name like the object. This is obviously more than one point, right? This comes together. All of these points, what would we call that? Melanie? A line, yeah. If two planes intersect, then their intersection is a line. Always two planes coming together are going to form a line at their intersection. So I have one more word that I forgot to put on here, so I need you to add it at the bottom, and that's coplanar. Just add it right at the bottom there, please. So just like collinear, this is coplanar. So coplanar is objects that can be contained by one plane, or on one plane, or in one plane. So this postulate right here, if two planes intersect and their intersection is a line, a couple of years ago, this was the very first question on the final exam. It was a fill in the blank, and it said if two planes intersect, then their intersection is a blank. You had to fill in the blank. The right answer was line. I had somebody put plane crash. Kind of true, right? But
someone actually wrote that?
Wrote plane crash.
They thought that was the correct answer.
No, I think they were just trying to be funny and they didn't know the correct answer. No, I didn't. Okay. No, it's not on the final anymore. Maybe I'll put it back. Maybe. All right. Okay, so I just want to talk about collinear and coplanar a little bit to make sure you understand this idea that if it can be contained by one plane, that it's coplanar. If it can be contained by one line, then it's collinear. So if I ask this question in our diagram here, are point A and point E collinear? Point A and point E, are they collinear? So generally people want to say no because there's no line that goes through them, but again, read the definition. Two objects that can be contained by the same line. Could I draw a line through points A and E?
Yes.
Yes, so then they are considered collinear. Okay, so can be contained. Same idea with coplanar. You know, if things can be contained by the same plane, even if that plane's not drawn, then it's considered coplanar. Array. Array is a part of a line Nope. With one endpoint. Oh, thank you. So it has one endpoint and goes forever in one direction. So let's highlight a ray here. I'm going to start at point B, and I'm going to go this direction. That's a ray. It has one endpoint and then an arrow that goes forever in one direction. Now, to name that, the proper notation, the first letter is always the endpoint, meaning the point that doesn't have the arrow. So what's the endpoint of what I highlighted there? So we're going to write that first. And then you're going to pick any point that ray goes through. So this goes through E. And then the symbol is line on top like we did with line that had two arrows. This time it's only going to have one arrow, and it's always going to be pointing to the right. No matter which direction your ray is facing in your diagram, it's going to be pointing to the right in your symbol, your notation. Okay, so let's take this ray. How could you name that ray? How could you name it? Kyle?
You could do CA or CB.
Good. So start at C, goes through point B, and continues past B. You see sort of the logic of that notation? Starts at C, goes through B, continues past B. Right? That same ray can also be named start at C, go through A, and continue past A. It's the same exact ray. Do you guys see that that's two ways of naming the same ray? If there were more points on there, we'd have more ways of naming it. Yeah.
What if there are no points? Like you start at C and you go.
So that's a good question. If there are no points, like for example, if you wanted to name like this ray, right? We have a D there. We don't have a. You actually would have to add a point in there to do it.
Are you allowed to add a point in?
Yeah, I mean, if you have to. If you have to, then yes. Okay, so an angle. An angle is the space between two rays with a common endpoint. So I know that you've heard of an angle before. You might not have defined it that way before. I want to show you my fan to tell you how. Notation for an angle. There are lots of ways actually to name an angle. There's 3 ways to name an angle. Most commonly, we're going to name an angle with 3 points using the vertex, which we're going to define in a second, as the middle point. So if I think I'll erase this so you can see better what I'm doing. If I'm going to name, let's say, this angle, right? That angle right there. I'm going to use 3 letters. You want to do it? Good. Angle A, B, D. And you're going to use this little symbol that looks like this, angle A, B, D. Can you name that same angle a different way?
DBA.
Good. Angle DBA. So those are the only 2 ways of correctly naming this angle in this diagram. And I always think about it kind of like you're giving directions, like go down the street, at the corner take a left. It's kind of like that. Start at A, get to B, and then turn and go through D. So you're kind of giving directions as if the person is going to trace that angle or the rays of that angle, right? So that's one way, 3 letters. That's the most common way. The vertex, by definition, is the common endpoint. In an angle. Oops. So vertex always has to be that middle letter if you're using the 3 letters. Okay. Bless you. Okay, sometimes you have a diagram that has numbered angles. You see this diagram down here? Angle 1, angle 2, angle 3, angle 4, angle 5. So sometimes they'll use little numbers right inside the angle to designate which angles they're talking about. Sometimes it's a little less confusing than all the letters. So that's a second way of naming it. The third way is by using only the vertex letter. But that is really reserved for very simple diagrams where literally the only angle at that vertex is the one angle that you're talking about. If you look at the diagram that we have here, if I said angle B, would you know what angle I'm talking about? No. So in this diagram, that's not an option. If there was a diagram where, you know, there's only one angle at point A, well, then you can do it. Okay, so that's a very specific case. Okay, notation here. If you have a little m and then the angle symbol, that is read as the measure of angle. And then you could have an equal sign after it because that's going to represent an actual degree measure. The measure of angle, whatever. So if we look at this diagram, you guys have protractors on your desks. Can you please measure for me angle ABD? So see what you get. Angle ABD. Okay, approximately 130, right? You might have gotten a little bit, give or take, but approximately 130. Let's use 130. That's a nice, easy number. Let's fill that in here. 130 degrees. What would you expect the measure of angle DBC to be?
50 degrees.
Why? Yep, go ahead. That's okay. 50 degrees because why?
Because they're both on the same line, and they're both on the same line, and so in order for them to be angles that are, they have to equal, because that line equals 180.
All together, they would have to be 180. Right, so if this is 150, that would have to be 30. All right, the next one is ABE. How many degrees would you expect ABE to be? Also 50, good. And then CBE, 130. Okay, I'm going to skip down a little bit. Adjacent angles. What does adjacent mean? Sam, right? Sam? Yeah. Next to. Right next to each other. Okay, so there's going to be some criteria for adjacent. I'll put next to. But technically speaking, the definition has to include 3 parts. 2 angles that, 1, have the same vertex, 2, share a side, share a ray, let's say, a ray or a side of the angle, and 3 have no overlap. Let's just say no overlap. So adjacent, right next to, literally your next door neighbor. If you imagine a backyard, some of you might have this situation where you have a backyard and then there's like a fence and then there's your neighbor's backyard, right? That's how mine is, right? I would say my yard is adjacent to my neighbor's yard because it's right next door. Literally, we share a property line. So adjacent angles literally share a ray. It's like this is the fence between the two neighbors. Okay? So if we take these examples, angle 1 is adjacent to, all right, so here's angle 1. What are the two adjacent angles to angle 1? The two next door neighbors. Bella? Nope. If we take this angle 1, if this is the fence, what angle is the neighbor? 3. Good. And then what's the on the other side? Nope. So angle 1 is adjacent to angle 3. So next door neighbor on one side is 3. What's the next door neighbor on the other side? Exactly. Good. All right, so what about angle 5? If angle 5 is the angle we're talking about, what are the two angles that are adjacent to angle 5? Emmy? 2 and 4. Good. That makes sense? Next door neighbor on each side. Good. Okay, so this is a really important, this is like our first postulate that we are going to apply and use a lot. And there's going to be so many more that we learn, but this is our first one. So, yes, I know. The angle addition postulate says, if you have adjacent angles, the one angle, the measure of one of the angles, plus the measure of the adjacent angle, equals the measure of the entire angle that they form.
Really?
Does that make sense? Seemed obvious? Okay. So if this was 20 degrees and this was 50, well, looks like more than that, 30 degrees and this was 70 degrees, then this would be how many degrees altogether? 100 degrees, right? Okay, so this is an example of the angle addition postulate. The measure of angle RYW, that's this one, plus the measure of angle WYZ, that's this one, equals the measure of angle RYZ, that's the entire thing. Okay? Now, that may seem obvious to you. It may not. But the important thing here is applying the skills that are going to take you all the way through June. Oftentimes, you're going to be given information kind of in a list like this. You have got to get into the habit of labeling your diagram really carefully with the given information. So this says angle RYW is 5x squared minus 2. RYW. I'm going to find RYW, and I'm going to label it 5x squared minus 2. Measure of angle RYZ. RYZ. Be careful. Which one is RYZ? The big one. And we're going to label this 10x squared minus 7x plus 7. And then WYZ is this expression here, 7x squared minus 2x plus 6. Now our job is to write an equation using that information. What would be the equation you could write? Check.
5x squared minus 2 plus 7x squared minus 2x plus 6 equals 10x squared minus 7x.
Kind of ran out of space, but that's okay. We'll borrow from the next column. No, Reason won't mind. Reason is very reasonable. Okay, so now we have our equal sign here, and we are going to solve this equation algebraically. 5x squared and 7x squared, all on the same side of the equal sign, so we just combine like terms there. We have a minus 2x and no other x terms on the left. And then we have a negative 2 and a positive 6, so that would be plus 4 equals this 10x squared minus 7x plus 7. If we're going to solve for x, what are we going to have to do? Emmy? So 10x squared. Good. What else do we have to do? Add the 7x. What else do we have to do? Subtract the 7. Because we need this all to equal 0. Why? Because what do we have to do? Factor. Yes. And use the zero product property. Yes. When you have an x squared and an x term, you cannot isolate one without factoring. Okay? So you have to factor a problem like this. So we're going to get everything to one side and 0 on the other side. 12x squared minus 10x squared is 2x squared. Negative 2 plus 7 is a positive 5x. Positive 4 minus 7 is a negative 3. It's one of those complicated ones that has the number out front. So to factor this, we're thinking what multiplies to what? Negative 6. Good. And adds to 5. So what could it be? If I add those, I'm going to get a negative 5.
6 and negative 1.
6 and negative. No, negative.
6 and negative 1.
Positive 6 and negative 1. If I add those, I'll get a positive 5. If I multiply them, I'll get a negative 6. That's good. So now we're going to keep the first term, keep the last term, and split that middle term into a positive 6x minus 1x. Now we find the GCF of each half of these. What's the GCF over here? 2x. So we're left with x plus 3. What's the GCF here? Negative 1. X plus 3. Those match, so we have x plus 3 is one factor, and 2x minus 1 is the other factor. So we have to figure out what x is then. X could either be negative 3 or positive 1/2. Now, in algebra, those would be your two answers. You'd have two solutions. In geometry, we have to check and see if those solutions make sense in the diagram. Nope. Because if we have an x value that makes our angle measure come out negative, is that okay? No. Right? You can't have a negative angle measure. So sometimes the positive one makes it negative, believe it or not. Sometimes the negative one makes it negative. Sometimes they both work. And then you have two answers. But in geometry, you have to take the time to check those. I know.
We would do that.
What?
Or we don't.
So you just plug it in.
Okay.
And you honestly don't even have to come up with the actual answer. You just have to figure out if it's positive or not.
Okay.
Do you know what I'm saying? So if I take the negative 3 and I plug it in here, use it different, right? If I put a negative 3 and it's squared, then is that going to be positive? Yeah, so I don't have to worry about that. And then negative 7 times negative 3, that's going to be positive, so that's going to turn out positive. I don't really have to figure out what the degree measure is unless I ask for that, but I don't really have to. Okay, if I plug it in here, still positive, minus 2, chances are, right, that's 9 times 5 is 45, and that's going to be positive. This is going to all be positive. So this one works. What about a half? Is that going to work?
No.
1/2 squared is, this one's a little trickier. So 1/2 squared is 1/4. So we've got 10 over 4 minus 7 over 2, which is what, 14 over 4. Right? Plus, okay, 28 over 4. That's good. 10 minus 14 plus 28, is that positive? Yeah, so that works, right? So then we would plug in a half here, and we would see if that worked. 1/2 squared is 1/4. 5 times a fourth is 5/4. Minus 2, does that work? That's negative.
Yes.
Right? So this one doesn't work. So we only have one solution. X is -3. Okay, so actually, there's not much space here, but the reason this is actually important, this column refers to what postulate or theorem or definition justifies that equation that you wrote.
Angle, addition, postulate.
You got it. So in the reason column, you should write angle, addition, postulate.
Good to remember the names of postulates.
Yep. You will, though.
I don't understand the word postulate. It's like postulate.